Hello everybody, me again, and this time with a lesson on the last class of transformations that we will work on, which is stretches and compressions. So the first thing I'm going to talk to you guys about is vertical stretches. And just for fun, I decided for this example to look at the cube root of x. Some of you might have seen Ariana posed the question in our discussions, what is that 3? What would the graph look like? And I thought, well, this is great. Let's look at it. Let's talk about it. So again, we are talking here about the cube root of x. That 3, this one here, that's not an exponent. That's actually the index of the radical. And what it tells us is what kind of radical it is. So the square root is the most common radical, so most of the time when we talk about it, we don't include an index, although you'll see on some calculators they actually include the 2 as the index. So you can write it if you want, but generally we leave it off. So the cube root of x asks us, what would you cube to get x? So let's label a few points on the graph. For example, what would you cube to get 0? Well, 0. 0 cubed is 0. So that's why this graph passes through the point 0, 0. What would you cube to get 1? Well, 1. So this graph passes through the point 1, 1. You'll notice that from there, we don't cross through a lot of super nice points. For instance, here, I'm just picking this one at random. The x-coordinate is 4. You all can see that the y-coordinate is a little bit bigger than 1.5. It's between 1.5 and 2. That's an irrational number. It's the cube root of 4. So square roots and cube roots, most radicals, in fact, all radicals, mostly their values are irrational. So the next nice point happens at 8, because 8 is the next perfect cube. The cube root of 8 is 2. The other thing that's really cool about the cube root is that unlike the square root, it doesn't have problems with negatives. If you square a negative number, you get a positive one, but if you cube a negative number, you get a negative number back. So if you ask the question, what would you cube to end up with -1? Well, the answer is -1. And over here, my graph cuts off, but I'll just put the point there for good measure. If you ask the question, what would you cube to end up with -8? The answer is -2. Okay, so there's the shape of the graph. And now you see I've already got a couple things prepared for us to think about. We're actually going to look at 2 functions this time, blue and red. In blue, we have 2 cube root of x, and in red, we have 1/2 cube root of x. So let's start with the blue first. And I've got the values table over here to the right, so I'm going to just pick a few values of x. You can do more if you want, but for the same reasons that we talked about with square roots, I'm going to keep it to nice numbers. So you'll notice I'm only using perfect squares here. All right, so if x is -1, g of x is 2 times the cube root of -1, which is 2 times -1. Oops, I accidentally put a little negative there, so let's erase that. Start over. Okay, so this is 2 times the cube root of -1, which is 2 times -1, that's -2. So the point there is -1, -2. For 0, you have 2 times the cube root of 0, which is just 2 times 0, which is 0. So the blue graph will pass through the origin as well. For 1, you have 2 times the cube root of 1, which is 2 times 1, which is 2. So that's the point 1, 2. And for 8, you have 2 times the cube root of 8, which is 2 times 2, which is 4. So there are our 4 points. So let's label them here. We have -1, -2. And when I said label, I really meant plot. I don't want to plot them and label them because then my graph will get really convoluted. So I'm just going to mark the blue points. So there I have the first 3, and then 8, 4 is there. If you want, you can kind of do -8 for yourselves. It'll be -8, -4, so that's about there. I'm just going to mark it lightly. Okay, so let's graph this in. And like before, we're just going to try to do our best. Right, so there is that part of the graph. And then here, same thing. And what I'm hoping by now you're starting to get a little bit of a feel for is that the original graph was symmetric about the origin. So the transformed graph should be symmetric about the origin too. All right, so now you have it there, the black graph and the blue graph. The blue is the one that's transformed, and you'll notice here I have this little fill in the blank. The graph of g of x is the graph of f of x. So the way that we're going to describe this relationship is we're going to say stretched by a factor of 2. Stretched vertically by a factor of 2. So I'm just going to say by 2, or you could say twice. And much like we did before, I want to take a second and I want to talk to you all about sort of the general case. So let's pick a random point here on the graph. I'm not, like, it looks like its x-coordinate is 6, but I don't care about that. So I'm going to say its x-coordinate is whatever. Let's call it x. And again, because it's a point on the graph of the function, it's an input-output pair. So the y-coordinate is f of x. So now let's dot from there. And there is the point to which that point maps or transforms. They have the same x-coordinate, but what about their y-coordinates? Well, the y-coordinate of the blue point is twice the y-coordinate of the black point. So on the one hand, the y-coordinate is g of x, and I'm going to write this in the summary. Actually, no, I'll write it here off to the side. We'll write g of x is equal to 2 times f of x. Okay? So that's what we're seeing to be true in general, that the outputs that the function g assigns are double the outputs that the function f would assign to the same inputs. All right, so let's go over here and let's look at the red function. And same thing, we're looking at 1/2 the cube root of x, so I'm going to pick a few values. And again, I'm going to do -1, 0, 1, and 8. You could also do -8 if you wanted. And then h of x is 1/2 times the cube root of that. So this will be 1/2 times -1, that's -1/2. So the point is -1, -1/2. For 0, you have 1/2 times the cube root of 0, which is 0. So again, the red graph will also pass through the origin. 1/2 times the cube root of 1. The cube root of 1 is just 1, so that's 1/2. And then for 8, 1/2 times the cube root of 8. That's 1/2 times 2, that's 1. So passes through the point 8, 1. So let's label those points. And again, I'm not going to actually label them. I'll just plot them to keep my graph from being too convoluted. So here is -1, -1/2. There's the origin. There is 1, 1/2. And there is 8, 1. So I'm sort of hoping that you're seeing, oh, this is the same exact shape, but just like smushed down. So I'm going to do my best here. So there is that graph. And again, if you wanted, you could plot -8, -1 down there, just to kind of give yourself a point of reference. So there is that graph. So you might already be kind of one step ahead of me here, but down in the summary where it says the graph of h of x is the graph of f of x, compressed, or smushed. If you prefer the word smushed, then you use that. Compressed vertically by 2. Okay? And similarly, I don't really want to do it on the graph here, but I will, and I'll hope that it won't kind of make things too claustrophobic. If I look here at some point, let's call it x, f of x, right? So some random point, I'm not worried about what it is. And then I kind of dot to the point on the red graph, which is the point that that black point transforms to. What I'm seeing is these 2 points have the same x-coordinate, but the y-coordinate of the red point is half of the y-coordinate of the black point. So on the one hand, the x-coordinate is x, y-coordinate is h of x, because it's the graph of a function input-output pair, but what we're seeing is that h of x is 1/2 f of x. So down here in my big summary box, which is still blank, I'm going to write what I hope we've all observed together, which is that the graph of c times f of x is a vertical stretch or compression of the graph of f. If c is greater than 1, like 2, it's a stretch. If c is less than 1, like 1/2, it's a compression. So this is how vertical stretches and compressions work. All right, so now let's go over here, and you'll notice I have a lot prepared for this piece of our discussion also. This is horizontal stretches and compressions. So same exact thing, but thinking about it horizontally. All right, so you'll notice this time, if I get my little laser pointer out here, we're starting with the square root of x, which is a familiar shape. We've worked with it before. And this time, instead of multiplying on the outside by a constant, I'm multiplying on the inside. So I have the square root of 2x. So I've multiplied x by 2. So in other words, in function speak, I am doubling the input rather than doubling the output. And then with h of x, I have the square root of x over 2. So I'm multiplying the input by 1/2. Rather than multiplying the output by 1/2. So let's go over here into our value tables. I'm hoping that by now we're pretty comfortable with the square root of x, and you will all agree with me that my values cannot be negative because the domain of the square root of x is strictly greater than or equal to 0. And then I'm going to take a few values here. So if we start with 0, 1, and 4, look what happens. When I go to plug this in, for 0 it works out. I have the square root of 2 times 0, which is 0. So the square root of 0 is 0, so okay, that's cool. But then if I go to do 1, I mean, it's not a huge deal. I'll get the square root of 2 times 1, which is the square root of 2. Like, I could plot that, but it's not a rational number. It's 1.4 something, something, something. So, not great, right? So, rather than picking perfect squares for x, maybe I should be thinking about what values of x become perfect squares when you double them. So, case in point, if I let x be 1/2, 2x will be 1. Oh, and the square root of 1 is just 1. So that gets me a nice point. If I let x be 2, right? 2 is another number whose double is a perfect square. 2 times 2 is 4. Its square root is 2. And then if you wanted to do one more just for good measure, you could do maybe 4.5 or 4.5. Why? Because if you double that, you get 9. So that's 3. So 4.5, comma, 3. So let's see what we got here. We have 0, 0. The nice thing about this particular scale is that 1/2 is just one square. So I have 1/2, 1, 2, 2, and then 4.5, 3. Okay. So there is that graph. So again, same shape, but this time kind of smushed, okay? So what's a little bit hard to visualize, and this is one of those things that I have a hard time doing as like a quote-unquote online instructor. If I was in front of you face-to-face, I could gesticulate and move my hands around. But this time I'm going to try to indicate this with a laser pointer. It's as if we took all of the points on the graph of F and we hurried them in this way, right? We kind of push them inwards. So what you actually see here, and some of you might be seeing something else, and I'm going to comment on it, but the graph of g of x is just like the graph of f, but compressed inward. Compressed horizontally by 2. Okay, so the way that I'm going to illustrate this is I'm going to pick some random point on the graph of f. So let's take this one. Let's call it x, f of x. And then we'll go sideways. So there's the blue point that black point got transformed to. And what I hope you all can see here is that the blue and the black point have exactly the same y-coordinate. But the x-coordinate of the blue point is half of the x-coordinate of the black point. So the x-coordinate of the blue point is x over 2, okay? So the y-coordinate, therefore, is g of x over 2, okay? And so the way that we're going to write this, because remember, we're trying to express g in terms of f, the way that we're going to write this is we're going to say g of x is equal to f of 2x. In other words, in order to get the same output, f needs to take double the input. So in order to find a point on f that has the same y-coordinate, you need to take a point whose x-coordinate is double what it was with g. So you see here, when you replace x with 2x, that's actually a horizontal compression. Let's see what happens in the red graph, right? So same thing. I've got my table of values going here. So let's see, if x is 0, then everything is fine. 0 divided by 2 is 0. So the square root of 0 is 0. So this point is the origin. Okay. Now, same thing, right? If I took x to be 1, 1 over 2 is a half, and the square root of 1/2 is some big old mess. So for my values of x, I'm really going to focus on numbers whose half is a perfect square. So for example, half of 2 is 1. That's a perfect square. Okay, the square root of 1 is 1. So the red graph will pass through the point 2, 1. Again, if I let x be 4, well, 4, half of that is 2. That's not a perfect square. So whose half is a perfect square? 8. Half of 8 is 4. And the square root of, the square root of 4 is 2. So the point here is 8, comma 2. If you want to do others, you can. For my purposes, I'm not going to because the next number, half of which is perfect square, is 18. And I don't have space for that on my graph. Okay, so here we go. So we have 0, 0. We have 2, 1. And then we have 8, 2. So there we go. Again, I'm focusing on the same basic sort of shape. Okay. So what I'm going to try to convey with my laser pointer here is that the red graph looks as though you took the black graph and you stretched everything that way. So you pulled it outward. All right. Now, again, some of you might be thinking, wait a minute, can't you think of it a different way? And yes, you can, but hold that thought. I'll get to it in a second. So the graph of h of x is just like the graph of f of x, but stretched horizontally. By 2. Okay. So let's look here. So let's look at a point on the graph of F, I guess. Now let's start with a point on the graph of H. So here's a point on the graph of H. We'll say that its coordinates are x, comma, h of x. And then let's dot over to the point that this point came from. Right? So the black point and the red point have the same y-coordinate, but I want you to notice that the x-coordinate of the black point is half of the x-coordinate of the red point. So the x-coordinate is x over 2. The y-coordinate is f of x over 2 because it's a function. Every point on the graph of a function is an input-output pair. But the black and the red point have the same y-coordinate. So we see here that h of x is equal to f of x over 2. So in other words, if you replace x with half of x, you end up with a horizontal stretch. If you replace x with 2x, you end up with a horizontal compression. So in my big, beautiful summary box that I have sort of at the bottom of the page, I'm going to write replacing x with c times x results in a horizontal stretch or compression, depending on the value of c. If c is greater than 1, f of c times x is a horizontal compression of f of x. If c is less than 1, f of c times x is a horizontal stretch of f of x. I'm going to put a thing here that I will leave 100% kind of for you to explore, and it'll be just a just kind of something for you to think about, and if you're curious about it, kind of like the way Ariana was curious about the graph of the cube root, by all means, post a discussion and we can talk about it. It seems that a horizontal compression can also be thought of as a vertical stretch. And a horizontal stretch can also be thought of as a vertical compression. So if you have that nagging thought, you are onto something. The reason that we don't really stress this very much is that, yes, a horizontal compression by a factor of 2 could also be thought of as a vertical stretch, but it's not a vertical stretch by a factor of 2 necessarily. It's a vertical stretch by a factor of something that is going to be dependent on what the function is. So that's why we call this a horizontal compression, because it's consistent regardless of what function I use, whether it's the square root of x or absolute value of x or x squared. When you replace x with 2x, that's always going to be a horizontal compression by 2. Whereas if you tried to also describe it as a vertical compression, it would be different. Vertical compression by how much? 2 or square root of 2 or 4 or what. So that's why we call these horizontal stretches and compressions, even though you could also come up with a way to describe them as vertical stretches and compressions. If that last bit was confusing, you could either ignore it, you could noodle it some more, and you can ask me a question in discussions. So that's it for this lesson. Stay tuned for more. Bye.